Welcome to the Public Exam Review Support for Advanced Math 3200. We will begin with Chapter 3 in Unit 1 on polynomial functions. In this presentation, we will discuss the characteristics of polynomial functions. We will focus on identifying polynomial functions and analyzing polynomial functions. To begin, let's look at the linear function, which is of the form y equals ax plus b. We will examine linear functions when the leading coefficient a is greater than 0 and when the leading coefficient a is less than 0. Note that for all linear functions, the degree of the polynomial is the highest power of x in the function. And when you have a to the x, that's the same as ax to the 1. So we say that the linear function is of degree 1, which is of odd degree, since 1 is an odd integer. In the two examples, we have a greater than 0, where the line slants upward to the right. And when a is less than 0, the linear function has the graph of a line slanting upward to the left. Let's look at the two examples. In the first function, we have y equals 2x minus 1. The degree of the function is the highest power of x. So x to the power of 1 is the degree of the function. The leading coefficient is a equals 2, which is the coefficient of your linear term. The shape of the graph in this case is a straight line, and that will be true for all linear functions. The end behavior of the function can be described as a line that extends up into quadrant 1 and down into quadrant 3. For the other linear function, y equals a negative x plus 3, the leading coefficient is less than 0. So we say that the degree of the function is again 1, because x is to the power of 1. The leading coefficient is a equals a negative 1. The graph is again a straight line, but this time because the leading coefficient is negative, the line slants upward to the left. To describe the end behavior of the function, we say that it extends up into quadrant 2 and down into quadrant 4. This will be true for all functions. When the leading coefficient is greater than 0, the graph will always extend up into quadrant 1. No matter what function you are working with, when the leading coefficient is less than 0, the function will always extend into quadrant 4. It's important to remember that. With regard to the quadratic function of the form y equals ax squared plus bx plus c, we have a polynomial function again, where the highest power of x is 2. So we say that the degree of a quadratic function is 2. And because 2 is an even number, we say that the quadratic function is of even degree. When the leading coefficient is greater than 0, your parabola will open upward. When the leading coefficient is less than 0, your parabola will open downward. Let's look at the two examples. In the first graph, we have the function y equals x squared plus 2x minus 3. The degree of the function is 2. The leading coefficient in this example is 1, and the shape of the graph here is a parabola that opens upward. This will always be the case when a is greater than 0. And to describe the end behavior of the function, note that the graph extends up into quadrant 1 and up into quadrant 2. For the other function, we have a parabola that opens downward. This function is given by y equals a negative 1/4 x squared minus 1/4 x plus 3. And that's the function that you see graphed here. The degree of the function is again 2. The leading coefficient in this case is a negative 1/4. And note that because that value of a is less than 0, we have a parabola that opens downward. To describe the end behavior of the function, it extends down into quadrant 3 and down into quadrant 4. Let's continue with the cubic function. A cubic function is of the form y equals ax cubed plus bx squared plus cx plus d. The highest power of x in the function is 3. So we say that the cubic function is of degree 3, which is again an odd integer. So the cubic polynomial is of odd degree. We have two situations again. When the leading coefficient is positive, your graph will extend from quadrant 1 and down into quadrant 3. When the leading coefficient is negative, a is less than 0, your graph extends up into quadrant 2 and down into quadrant 4. Note that the shape of both of these graphs represents a sideways F. So let's look at two examples. In the first case, we have the function y equals x cubed minus 5x. The degree of the function is 3. The leading coefficient in this case is 1. And the shape of the graph is what we refer to as a sideways F. The end behavior of the function, it extends up into quadrant 1 because of the positive leading coefficient, and down into quadrant 3. In the second example, the leading coefficient is negative. We have the function y equals a negative 2x cubed plus 4. Note that the degree of the function is 3. The leading coefficient in this case is a equals a negative 2. The graph is still a sideways F. And to describe the end behavior of the function, it extends up into quadrant 2 and down into quadrant 4. This will always be the case for any function that has a negative leading coefficient. The graph will always extend into quadrant 4. I find that that's an easy way to remember it. If a is greater than 0, you are in quadrant 1. If a is less than 0, you will be in quadrant 4. To continue, we have the quartic polynomial. So the quartic function is of the form y equals ax to the 4 plus bx cubed plus cx squared plus dx plus e. The highest power of x is a 4, so we say that the quartic function is of degree 4, which is again an even function. Two examples, one where a is greater than 0. Note that the graph extends from quadrant 1 up into quadrant 2. When a is less than 0, the graph extends into quadrant 3 and into quadrant 4. The degree of the first function, y equals x to the 4 plus x cubed minus 17x squared minus 21x plus 36. The degree of the function is 4. The leading coefficient, a, is equal to 1. The shape of the graph. When a is greater than 0, note that the graph is in the shape of a W. So it's in a W-shaped graph, and the graph extends up into quadrant 1 and up into quadrant 2. In the other example, we have the function y equals a negative x to the power of 4 minus 4x cubed plus 17x squared plus 60x. The degree of the function is 4. The leading coefficient in this example is a negative 1. And because the value of a is less than 0, the graph of the quartic function will be in the shape of an M. The graph extends down into quadrants 3 and 4. And finally, we have the quintic function, which is of the form y equals ax to the power of 5 plus bx to the 4 plus cx cubed plus dx squared plus ex plus f. The highest power of x is 5, so we say that the quintic polynomial is of degree 5, which is of odd degree. Note that when a is greater than 0, the graph extends up into quadrant 1 and down into quadrant 3. When a is less than 0, the graph extends up into quadrant 2 and down into quadrant 4. Let's look at the two examples more closely. In the first example, we have y equals x to the 5 minus 3x cubed plus 2. The degree of the function is 5. The leading coefficient in this example is 1. In terms of the shape of the graph, there is no particular shape, so I make reference to it as being in the form of a squiggle. The graph extends up into quadrant 1 and down into quadrant 3. In the second example, we have the function y equals a negative 2x to the 5 plus 5x cubed minus x, graphed here. The degree of the function is 5. The leading coefficient is a equals a negative 2. Again, it's in the shape of a squiggle. And we say that the graph extends up into quadrant 2 and down into quadrant 4. So those are the characteristics of each of the functions: linear, quadratic, cubic, quartic, and quintic. Let's look at some examples. In the first example, what is the degree of the polynomial function p of x equals 3x to the 4 minus 2x cubed plus x to the 5 minus 7x plus 1. I suggest at this point that you put the polynomial in descending powers of x, so that your leading term would be x to the 5 plus 3x to the 4 minus 2x cubed minus 7x, there's no quadratic term there, plus 1. And we see here that the highest power of x in the polynomial is 5. So that tells us that this polynomial is of degree 5, which it would represent that of a quintic polynomial. So the correct answer for the degree of this polynomial is D. It is of degree 5. Another example, we are given 4 multiple choice items, which is a polynomial function of degree 2. In the first example, we have what is referred to as a radical function. A common mistake that students make with this type of a polynomial is as follows. You need to note that the square root of x to the 4 minus 9x squared does not equal x squared minus 3x. This represents a radical function which is not a polynomial function. The radical function contains a square root sign, and that is not representative of a polynomial function. In part B, if you put the function itself in descending powers of x, you would see that the highest power of x in that function is 4. So this polynomial function is of degree 4, and we're looking for a polynomial function of degree 2. For part C, you need to recall your rules for exponents. I would like you to note that 1 over a to the negative m is equal to a to the positive m in terms of your rule for exponents. So to rewrite this polynomial function, 1 over x to the negative 2 is the same as x squared, minus 3x minus 9. Note that the highest power of x is 2, so we can say that this polynomial function is of degree 2, which represents a quadratic function, and that's the function we're looking for in this example. So the correct answer here would be C. And in the last example, we can eliminate that as a multiple choice answer because the highest power of x is 3. So we say that this polynomial is of degree 3, which again does not satisfy the condition that needs to be met. In the next example, which polynomial function has degree 2 and a positive leading coefficient? So the first key piece of information that we need to recognize is we're looking for a polynomial function of degree 2. If the function is of degree 2, then it must be a quadratic function. And a quadratic function, you would be looking for a parabola. The graph is a parabola. So that eliminates C and D as possible multiple choice items. The next piece of information is that we need to have a positive leading coefficient. If the leading coefficient is positive, then the value of A is greater than 0, which means that the parabola should open upward. So the only correct multiple choice answer for this situation is A. In the next example, which is a possible equation for the polynomial function? As I look at the shape of this graph, I see that it's in the shape of a W. That tells me that we're dealing with a quartic function. Note that the graph extends up into quadrant 1 and up into quadrant 2. Because the graph extends up into quadrant 1, you know that the leading coefficient is greater than 0. That eliminates multiple choice answers A and C because these values of A are less than 0. In order to figure out what the factors would be in this case, you need to look at the possible x-intercepts. You have one value of x at x equals a negative 1. Therefore, the factor would be x plus 1 would equal 0. In the second case, you see another factor, another x-intercept at x equals 1. Therefore, you would have x minus 1 to equal 0. However, the graph is tangent at that point, which tells us that this factor will have a multiplicity of 2. So that means x minus 1 will be raised to the power of 2. That factor will occur twice. And in the third case, we have an x-intercept at x equals 3. Therefore, the corresponding factor would be x minus 3 equals 0. To look for the possible polynomial function, we would have y equals a outside of x plus 1 multiplied by x minus 1 all squared times x minus 3, keeping in mind that the value of a has to be greater than 0. So in this case, the function that corresponds with this situation would be b. Another example, which describes the end behavior of the function of a polynomial which describes the end behavior of the graph of a polynomial function that has two turning points and a negative leading coefficient. When we talk about two turning points, the number of turning points, I should say the maximum number of turning points that a polynomial function can have will always be one less than the degree. So if we have two turning points, then that means that the polynomial will be of degree 3, which is an odd degree polynomial function. If it has a negative leading coefficient, then the graph would, remember that the graph has to be a sideways S. And the graph of that sideways S has to extend down into quadrant 4, because A is less than 0, and because the graph is a sideways S, it would be up into quadrant 2. Just to draw a graphic representation of what's happening here, we are told that the leading coefficient is negative. So that means the graph has to begin here in quadrant 4. If you go up to form a sideways S, there's one turning point. Here's the second turning point, and there your graph would extend up into quadrant 2. The only situation that corresponds with this one is C. It extends up into quadrant 2 and down into quadrant 4. And in example 6, which is true for the graph of ax to the n plus bx to the n minus 1 plus cx to the n minus 2, and so on, plus d, to extend up into quadrant 2 and down into quadrant 4. I find it easier to remember down into quadrant 4 will guarantee us that the value of A, the leading coefficient, has to be less than 0. So that eliminates C and D as possible multiple choice answers. If the graph extends up into quadrant 2 and down into quadrant 4, the first graph that comes to my mind would be an S-shaped graph extending from quadrant 2 to quadrant 4, and that would be a cubic function, which is of degree 3, which is odd. So the correct answer would correspond with A in this situation. However, we do have another odd polynomial. Another odd polynomial could be that of a quintic, where we have the graph of a squiggle. Again, we could have, because it's of degree 5, it could have 4 turning points. So again, the graph extends from quadrant 2 to quadrant 4. So this would be the case for a quintic polynomial, which is of degree 5. And again, that's an odd degree polynomial function. And similarly, we also have the linear one as well. If we have a linear function, the linear function is of degree 1, which is again of odd degree. So in this case, your straight line would extend from quadrant 2 up into quadrant 2 and down into quadrant 4. So any polynomial of odd degree that extends from quadrant 2 to quadrant 4 would have the leading coefficient to be negative. To summarize what we've covered today, you can have a constant function, which is of degree 0, and it's considered to be an even degree. An even degree function with a degree of 0 has a maximum number of 0 x-intercepts. The function will not cross the x-axis unless it is the x-axis itself. So an example here would be f of x equals 3. Note that the end behavior extends horizontally from quadrant 1 to quadrant 2 if the constant is positive, and if it was from quadrant 3 to quadrant 4 if the constant was negative. The domain is considered to be the set of real numbers. The range would just be values of y equal to 3 in this case, and we have no x-intercepts in this example. The linear function is of degree 1, which is odd. The maximum number of x-intercepts is 1. So when you look at the x-intercept, it's right here. In this example, the line extends up into quadrant 1 and down into quadrant 3. The domain is all set of real numbers, and the range is all values of y belonging to the set of real numbers. And the maximum number of x-intercepts that any linear function will have is 1. A quadratic function is of degree 2. It's an even degree. You could have a parabola that has 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. In this particular example, we have 2 x-intercepts. The curve extends up into quadrant 1 and up into quadrant 2. The domain is any real number, but the range is dependent upon the location of the vertex. And in this case, the coordinates of the vertex are all values of y that are greater than a -3. All values of y that are greater than a -3, and y belongs to the set of reals. And in this particular case, the number of x-intercepts is 2. There will always be a maximum number of 2 x-intercepts for a quadratic function. For the cubic function is of degree 3, which is odd. You can have a possibility of 1, 2, or 3 x-intercepts. But note that a cubic function will always have at least 1 x-intercept. In this example, the curve extends up into quadrant 1 and down into quadrant 3. The domain are all values of x belonging to the real numbers. The range are all values of y belonging to the real numbers. And in this example, we have 3 x-intercepts. The maximum number of x-intercepts for a cubic polynomial is 3. For the quartic function of degree 4, it's an even degree. You can have 0, 1, 2, 3, or 4 x-intercepts. In this example, the function extends up into quadrant 2 and up into quadrant 1. The domain is the set of real numbers. The values of y are dependent upon the location of that minimum point on the graph. In this particular example, that minimum point in this function occurs at -6.91, which can only be determined using graphing technology. The maximum number of x-intercepts that any quartic function can have is 4. And for the quintic function of degree 5, which is odd, the number of x-intercepts can be 1, 2, 3, 4, or 5. Note that the quintic function must always have at least 1 x-intercept. And in this case, there is a maximum of 5 x-intercepts. The graph extends up into quadrant 1 and down into quadrant 3 because the leading coefficient is positive. The domain are all values of x belonging to the set of real numbers, and similarly for the range, all values of y belonging to the set of real numbers. And the maximum number of x-intercepts that any quintic function can have is 5. If you have any questions about this presentation, feel free to post a question in the question forum, and I would be happy to answer it for you. Thank you for your time and your attention.